This is the fifth lecture of the series of lectures entitled Solid Angle. We addressed few problems in the previous lecture 4, and in this lecture we shall turn our attention to Gauss' law of gravitation, which is a law of paramount significance. Statement of the law. The total outward flux of gravitational field vector E across a closed surface, call it S, is equal to minus 4 pi g times the total mass enclosed by S, where g is the universal constant of gravitation. Mathematically stated, we can put the law as closed surface integration of vector E dot vector ds, integration is over S, equal to minus 4 pi g times the total mass enclosed by the closed surface S. This is actually the outward flux of vector E, where vector E represents the gravitational field. Proof of the law is as follows. Consider a distribution of point masses. Let us imagine a closed surface S in the field of masses. These dots represent the point masses. Let this be the closed surface, call it S. This dot is a typical mass lying outside, and this dot is a typical mass lying inside. Obviously, some masses lie inside and some lie outside. We consider the gravitational field at a point P, the position vector of which is vector r, due to a source mass m at point Q, the position vector of which is vector r prime. The gravitational field is denoted by vector E. Let O be the origin of system of coordinates. This is x-axis, this is y-axis, and this is the z-axis. Let this point represent point mass m. Let us name this point Q. This is the position vector of point Q. Call it vector r prime. Consider another point. Call it P. This is its position vector. Call it vector r. Join Q to P and define this vector. Call it vector capital R. And by triangle law of vector addition, vector capital R is vector small r minus vector small r prime. Let us highlight it. This vector capital R represents the position vector of point P with respect to point Q. Let us now write the expression of the gravitational field at the field point P created by the source mass m at point Q. It is minus gm by r square into r hat. So gravitational field at a point on S will be vector E equal to minus g mi by ri square into ri hat. This is the contribution of the interior ith mass mi to the gravitational field vector E. This means we have to sum over I. Plus, now we write the contribution of external jth mass, which is minus g mj by rj square into rj hat. This is to be summed over j. I and j are dummy indices or run indices. This portion is the contribution of interior masses to vector E, and the second term represents the contribution of the exterior masses to the gravitational field vector E. Outward flux of vector E across S is closed surface integration over S vector E dot ds equal to closed surface integration over S. Now put the expression of vector E, the gravitational field, dot vector ds. And vector ds is the surface element representing n hat into ds, n hat being the outward unit normal to the surface S. This is equal to summation over I minus g into mi into closed surface integration over S ri hat dot n hat by ri square into ds plus summation over j minus g into mj into closed surface integration over s rj hat dot n hat by rj square into ds. Let us focus attention upon these factors. The structure of these factors is closed surface integration over surface S r hat dot n hat by r square into ds equal to closed surface integration over S ds cosine theta by r square. This is equal to closed surface integration over S over d omega, which is the elemental solid angle. We construct cones with vertex as the point mass mi, a typical internal point mass, and with vertex mj, a typical external point mass. This is the closed surface S. This dot is the internal point mass mi. This is the cone with vertex mi subtended by the surface element ds. For future convenience of reference, let us label this ds by encircled number 1 and this cone by the encircled letter A. Let this dot be mj and we construct the cone with vertex mj subtended by the surface element ds here and another ds here. Clearly, we have to label them for identification purpose that we do now. This ds let us label by the number encircled 2 and we label this ds as the number encircled 3. This cone that has mj, the jth external mass as vertex, is labeled by the letter encircled b. Let us re-mention that such labeling of 3 DSs and 2 cones will help us in making future reference. This is the outward unit normal of this ds labeled as encircled 1. This is n hat of the ds labeled as encircled 2. And this is the outward normal of ds labeled as encircled 3. We now draw the radial unit vector ri hat from mi and the radial unit vector rj hat from mj. Next, we show the angles between r hat and n hat at the 3 ds's. This is theta between ri hat and n hat at ds labeled encircled 1. We see that this theta is acute, that is less than 90 degree in value. The theta at ds labeled encircled 2 between rj hat and n hat is also acute. But this theta between rj hat and n hat at ds denoted by encircled 3 is obtuse, that is greater than 90 degree. Theta is the angle between r hat and n hat. We have 2 types of elemental surface DSs. In one type we have DSs where cone leaves the surface S and theta is acute. This occurs as we have shown for cone labeled A at ds labeled by number encircled 1 as well as for cone labeled B at ds labeled by number encircled 2. Again, cosine theta is positive for theta acute angle. Hence, d omega equal to ds cos theta by r square, which we designate as mod of d omega, and it is positive. In another type, we have DSs where cone enters the surface S and theta is obtuse. This occurs as we have shown for cone labeled B at ds labeled by number encircled 3. Again, cosine theta is negative for theta obtuse angle. Hence, d omega equal to ds cos theta by r square, which we designate as minus mod of d omega, and it is negative. We have 2 types of cones. One type of cone is with apex mi, that is vertex lying inside the surface S, and they cut through the surface S odd number of times. In other words, cones starting from mi as vertex have odd number of cuts. Odd means 1, 3, 5, etc. crosses across S. In the diagram shown, the cone labeled encircled A and starting from mi cuts the surface S once at ds labeled by number encircled 1, and this cut or intersection is while the cone is exiting the surface S. It is going out of S. Consider integration d omega over the cone labeled by the letter encircled A. It is equal to mod d omega because theta is acute and we are referring to ds labeled by the number encircled 1. Now we integrate over S to get, let us write the integral over S. This S consists of numerous, rather infinite number of surface elements ds's, such as this one. Let us call encircled small a, which contributes 1 mod d omega, the elemental solid angle due to ds, where theta is acute. Plus another cone emanating from mi, the base being another ds, call it encircled small b, that makes a similar contribution of mod d omega. Then another one, call it encircled small c, that also contributes another mod d omega, and so on for all such ds's over the surface S. So it is actually a closed integration over all the elemental solid angles mod d omega. In other words, it is the total solid angle subtended by the closed surface at an internal point mi, and its value is 4 pi. We did it in lecture 3 of this series entitled Solid Angle. The unit is steradian. Clearly we have got 4 pi steradian as the contribution made by the internally located point mass mi. It is the solid angle at internal point. Let us now talk about another type of cone, the cone with apex mj that lies outside the surface S. It makes even number of cuts. Even means 2, 4, 6, etc. number of crosses across S. For instance, the cone labeled by the letter encircled B makes 2 cuts, one during entry at ds labeled by the number encircled 3 and another during exit at ds labeled by the number encircled 2. Consider the integration of our cone encircled B d omega equal to, let us write the contributions now. It is mod d omega, which is the contribution of ds labeled by the number encircled 2, at which theta is acute as cone B exits from S here. And then we have minus mod d omega, which is the contribution of ds labeled by number encircled 3, at which theta is obtuse as cone B enters into S. So the contribution at ds's at 2 points of cone B cancels each other out. Clearly cone B, I mean the cone starting from outside of S, do not contribute. Integration over S gives, we write the contribution of each such cone like the cone B, and clearly it is 0. So the cone starting at the external mass mj does not contribute. Clearly the external masses do not contribute to the flux of gravitational field over S. Closed surface integration of gravitational field vector E dot ds, that is the flux of gravitational field E, is, let us quote the expression that we previously wrote. This factor contributes a 4 pi, and this factor gives 0, does not contribute. So we have the right hand side summation over I minus g mi 4 pi, which gives minus 4 pi g times the enclosed mass. This is Gauss' law of gravitation. Clearly, the concept of solid angle leads to establishment of Gauss' law of gravitation, and we have showed this clearly. In the next lecture 6, we shall show a similar application of the concept of solid angle leading to Gauss' law of electrostatics, which is a law of immense significance.